Welcome to this podcast on mathematical model for cyclone intensity dynamics under climate change and optimal control strategy for mitigation.
This paper by Samanta, Dolai, and Mandal addresses a critical issue: the increasing intensity of tropical cyclones.
They highlight how rising global temperatures, specifically warmer sea surface temperatures, fuel stronger storms.
And this intensification is particularly pronounced in tropical and subtropical regions, leading to devastating impacts.
The authors note that traditional models often overlook the long-term influence of climate change and human intervention.
So, their study develops a new mathematical model to examine cyclone intensity dynamics under climate change.
It also proposes an optimal control strategy to mitigate these impacts, which is quite forward-thinking.
The model captures interactions between three key variables: cyclone intensity S, accumulated cyclone energy E, and sea surface temperature T.
Could you explain what accumulated cyclone energy or ACE represents in this context?
ACE reflects the storm's total energy, influenced by ocean temperature and atmospheric conditions, essentially its destructive potential over time.
And the model incorporates a control parameter, UW, representing global temperature reduction efforts.
Yes, like greenhouse gas reductions or ocean cooling strategies, to regulate sea surface temperature and control intensity.
How did they determine the optimal control strategy for this complex system?
They applied Pontryagins maximum principle, a powerful tool for finding optimal trajectories in dynamic systems.
The goal was to minimize cyclone intensity while ensuring the system remained stable, correct?
Precisely, they wanted to find the best way to reduce cyclone intensity without causing other instabilities.
The paper states the system's equilibrium points are both locally and globally asymptotically stable. What does that mean?
It means the system will naturally return to a stable state after any disturbance, ensuring the feasibility of long-term solutions.
Their sensitivity analysis identified key influential parameters. Which one stood out?
The stability criterion R4 was highly sensitive to N-prime, the saturation threshold for cooling efforts, with a 10% increase in N leading to a 5% increase in R4.
And parameters like mu, the dissipation rate, and beta PRZ, PMCT, 2, Prom Gaudenke, Karizude Large Commander, H. Wat Arkavanbar, H. Marske Ruder Kabelikar, Aflation, Mantar Zarmai.
Interestingly, phi prime, the rate of temperature increase due to climate change, and U prime, the control effort, showed low sensitivities for R4.
However, alpha, the energy transfer coefficient, and rho Pn, the energy extraction coefficient, were found to be most influential for cyclone intensity and energy evolution.
Yes, alpha drives cyclone strength through ocean-atmosphere energy exchange, and rho enhances long-term energy buildup.
They verified their model using numerical simulations, employing the fourth-order Runge-Kutta method in MATLAB.
These simulations compared fixed control parameters versus optimally applied control, revealing significant differences.
The results showed that adaptive temperature reduction strategies significantly outperform fixed controls.
This leads to lower cyclone intensity and enhanced system resilience over time, a very encouraging outcome.
The paper cites observations of a 13% increase in significant intensity tropical cyclones over the past 40 years.
And projections suggest TCs could be 9.5% to 17% more intense by the end of the century under different climate scenarios.
This research provides a robust framework for assessing how temperature regulation could influence cyclone risks.
It truly highlights the potential of targeted interventions to reduce the destructive power of tropical cyclones in a warming world.